Hello, good morning, good afternoon. My name is Bikash Choudhury. I'm a Director for Solutions focused on HPC, EDA, DevOps. And it's been great pleasure talking to the Korean community here, the 퓨어스토리지 Korean community in and around Seoul. Today we're going to talk about why Pure. That's been a question that can have a variety of answers. And we'll touch upon some of the key answers which could be relevant towards two things. Number one, we'll talk about EDA. That's something that has been very popular, and that is something which has been looked after or reached out, or we've got a lot of customers around here who are semiconductor design and foundries. And this is a good area to discuss exactly what is going on in the EDA space. And obviously, we will be talking something more about the product FlashBlade later on. Let's get started. All right, so the EDA obviously is broken up into two parts. One is the semiconductor design, and you have got foundries. The design is building the blueprint, and the foundries are the ones that manufacture them, right? Now, if you look at these the newspaper clippings that you see here on the screen, there are so many different news, and I'll just bring your attention to one of them, like where it says for the Intel Sapphire Rapids, right? Intel had $500 to fix in its next supercomputer chips. That's about Sapphire Rapids that got released last year. They pulled the chip back from the market, then fixed those bugs and really released again. Now let's look into the reason why this is happening, right? Let's unpack a few things. Now, I do not want to take an approach from a bottom up where we are trying to be more focused on the storage. Yes, storage is an important component. We'll talk about it as we move forward. But let's talk about the high level stuff, what exactly matters the most in the semiconductor and a foundry business, right? So obviously time to result is key, but along with that is quality of results and the cost of results. So in today's changing environment, because of the supply chain and a chip shortage challenges, it's a big demand on the cost. Now, when you look at the cost, let's unpack the term cost, right? When you look at cost is not just the cost about investment on infrastructure. It is not the investment only on the EDA tools. It is also the investment of resources, the manpower, the time it takes to run a particular project, the iterative nature of these projects to have a successful blueprint of a particular chip or a circuit that you're designing, right? So it is all about time to market. It's all about competition, who gets there first. Just like I was giving out the example of Intel with $500, yes, they did deliver the chip or tape out the chip, which is tape out is a semiconductor language in EDA term. So they taped out the chip faster because they want to beat the competition, but ended up withdrawing it or pulling it back from the market because they had so many bugs. So its quality is important because you cannot sustain in a market that is so dynamic with not a good quality, right? So your dev cycle, because every time you are going through the blueprint, there is got a development cycle. So you need to also look into the development part of that when you're talking about the register transistor logic transfer logic, the RTL, and how does it actually design, or how you design your flip-flops, your registers, and all of those kind of things. That is very important. And then obviously the scalability. That's the key, right? The elasticity of how you scale. I'll give you one thing though. In an infrastructure play, any semiconductor design or foundry would definitely claim, and this is true by the way, it's not their claim, but it's the truth, that they have got enough compute power in their data centers to overrun any storage endpoint. It's just not pure storage. It could be any storage, right? They have that power. But every hardware has its limit. We need to identify those limits and making sure that how long can you sustain a particular workload at scale under certain latency, because that's very important, because the faster you can deliver and faster you can complete the jobs that has been submitted in the queue, and how fast the storage is able to handle those kind of jobs, the latency in which the turnaround time is impacted for the end user or the design engineers who are working on it, that's very important. right? So let's look into some of the design trends today in the market. This is the data that was published by Intel. The links are below. You can feel free to read those articles. They constantly update them. I think this is the latest one that has been published recently. Now, if you look into this, the bar charts that you see on the right-hand side, you would see the amount of compute servers they have in the data center. Now, keep in mind, Intel do not go to cloud. They're completely 100% on-premise today. Now, the reason why I have this data from Intel is more or less all the semiconductor and foundry businesses today globally will have very similar trends and environments in their design and tape out in the data centers premises, right? So this data is just a representative to show what is actually the real thing happening within a data center. What's the trends that is happening? So when you're actually going to have a massive change in your infrastructure, when do you need that? That is happening when you are actually going down on the chip design. If you're going to a sub 10 nanometer design or less, like right now we are entering into angstrom, right? It is going to be 2 nanometer or 20 angstrom or less. So whenever you're going to that level, what happens is you generate a ton of more data. You do a lot of processing. So you're throwing in more compute. That means your jobs that are running is now doubling up or quadrupling. There's a high volume of jobs been submitted. Your project lifetime, everybody wants to shorten the lifetime. And then also, how do I actually run my jobs faster? Now, when I say faster, it is just not the software component. That's the tool, your IPs that you have, or the project data that you're using for that particular project. It's just not the software alone. It is the hardware's response time also is equally very responsible or important at that time. So what will happen is there is a lot of consolidation also happening in the industry. There is a mixed workload. If you look at the EDA workload, there is some part of the design process which has got a high amount of metadata. There is another part of the tape-out process which is more on throughput. There's a lot of large files, there's a lot of reads and writes happening. So if you look at this entire flow, you just cannot put a finger in any part of this workflow saying that this is the signature that you see for the entire workflow from the start of a design till the end of a particular chip that is being taped out and released into market. So the entire flow has got a very diverse workflows, and that is very important, is that how can an underlying infrastructure handle that? So that's the thing, because if you look into other HPC workloads, they are not as diverse. They would rather go high metadata, or they would go high throughput, and a lot of the workloads wins on throughput because, hey, I need massive amount of read and write. Whereas an EDA has got a very mixed workload, and that's very important to know. And the other one is, the last point is basically about the transition that is happening to cloud. Because all along we've been hearing about, oh, let's go to cloud, but there was a slow progress in the movement to cloud, but it is happening now. The reason because the design demands are so high about the compute requirements that the on-premise data centers are not equipped to handle those compute requirements on demand. Now they can actually move forward, getting more number of servers installed in the data centers, but in reality that is not possible when you're doing it on demand. When a project is live and active, you just want to move on with that particular testing process. So when you are slowing down the testing process by not enough compute nodes and you cannot acquire servers in time, then that is overall going to impact your delivery timeline. So what they do is they're now bursting into cloud. So the cloud can give them ample amount of compute resources. Now, how does it actually work out with the data? Because yes, you can spin up X amount of compute nodes in the cloud, but how do you actually get the data up there? And how does the storage component help there? So we'll talk about all of those things as we go through these different trends in the market today. Now, also, as I was talking about cost in the earlier slide, right? There is a reason why people are the businesses in the semiconductor design and foundries are so paranoid about cost, because it is just not the design complexity. Imagine the amount of time they would spend about a 16 or 17 nanometer, even a 300 nanometer chip. right? Which has been out there in the market, and then obviously that doesn't take that much amount of complexity, does not take that much amount of registers and flip-flops to program and work on. Whereas if you go down to like a 5 nanometer or a 3 nanometer, now into Angstrom, that means the design complexity is growing. And the turnaround time for those projects for chips that are so small is very important. And that is where it is driving the cost. Exactly what I told you is, yes, you can throw in as much more number of compute to that particular compute platform, but consider the amount of cost incurred from the power consumption, the heating, the cooling, and the overall carbon footprint that you have in the data center. That is the cost they're trying to reduce. They're trying to reduce the cost, the compute per watt. That's the term. They are trying to reduce the compute per watt and improve the performance per rack space. So that's important. That's the cost factor associated with that. Then there are short running jobs and long running jobs, depending on what part of the workflow you are working on. If you're doing verification, which is in the very early part of the chip design process, it'll be short running jobs, but there are millions of jobs going to be running. It's depending on the kind of a chip you're designing. It could be a queue that is running 24/7. Whereas if you go towards the tape out part of it, there was long running jobs. Now, how do I actually reduce the time? Just keep in mind, EDA license tools cost a ton of money. Yes, this is a big chunk of their budgeting goes towards EDA license tools. Now, how do I actually impact or influence or optimize the license cost? That is very important because we can't directly reduce the cost, but we can definitely try to optimize the cost. How can we do that? If we can finish the jobs much faster than any other storage endpoint, then we are saving them time. That means a project which was running 30 weeks, we reduce that to 20 weeks. That means we are giving them a benefit of 10 weeks where they can actually start another project. So that is how we optimize the EDA cost. This is one way of doing it purely on performance, right? If you are how fast you can finish a job. And there is another way of doing or optimizing the license cost for EDA tool licenses. I'll talk about that in a few slides later. But that is how we are directly optimizing the EDA tool licenses. And then slow infrastructure. Again, it's all about the elasticity of infrastructure, the provisioning part and the consumption part, so that you do not have the ability to slow down any particular project. Like, give you an example. If you're having more than one project running in a single storage resource or endpoint, and your project one has got a higher priority, that means it has got a tighter timeline for the deliverable, whereas you've got project 2 and 3 running, and at the same time they're hitting the same resources and they're consuming so much amount of resources that project 1 is starved out. So if that is the case, then obviously all the jobs that have been serviced by that particular project on the storage platform is going to slow down, and that is going to impact the overall deliverable of that particular project. So that is, again, very important to understand. The cost of that goes up. So just to summarize, what exactly are the key business requirements for EDA? First of all, scale more cores in compute form for incremental growth. Right, that is absolutely true. That is happening every day. When you talk to a customer today and you have another conversation later on, a few months out, you hear that, oh, we have already grown our compute by 10% or 7%. Right? There's a constant inclusion of compute. Second is, how do I actually grow my software delivery pipeline? That's another important thing, because there is a lot of software development that is happening. Keep in mind, in any vertical, including EDA, or you would like to talk about any other research or other HPC verticals, there is some cross-functional workloads that actually work horizontally. That is, software development is one of them. You find software development everywhere, because without that, none of your other workloads is going to be in existence, or that you cannot just be working with that, right? You need to have software development. So the objective is, how fast can you run that? And we are actually having a great solution for that. I will briefly touch upon that towards the end, but if anybody needs to know more about software development, please reach out to me directly and we can have a one-on-one conversation about that. Simplify storage management. The complexity is killing a lot of people because they do not want to be in the storage business. They would like to consume storage. They would like to get the performance for the data that has been written or read from the storage, But other than that, they don't want to go through a learning curve on the storage platform. They don't really want to be a storage admin because the personas are evolving. You don't see a storage admin anymore. You probably will be having an IT architect or a DevOps admin, right? Whereas you don't see a storage admin. They are the incumbents. They are starting to be obsolete. Those personas are slowly starting to dry up. You normally don't see storage admins in existence that many. There are few traditional companies who still have them, but most of them are gone. Deliver design faster. That is exactly the reason why we are looking and focusing as to how do we reduce the job completion time, the turnaround time. That's very important. Provide scalable and efficient performance, and that's where when you are adding more number of compute at the top layer in the compute platform, how does the rest of your infrastructure support that? The networking. And believe me, I bring up networking because in a couple of slides, I'll show you the bottlenecks. Network is a bottleneck. A lot of customers who are running on 1 gig connection from the host, which is gone. So they should be moving to a 10 gig or more. So network is going to be a bottleneck. The switches are old. The firmware are not upgraded. We can't just discount that part because they are also part of the same data path, right? So when you are having any hardware sitting in the data path, that could be a potential bottleneck right there. And then mobilizing data for more hybrid cloud, that's another important thing. I was talking about the trends in the previous slide, that data, and so the business is now moving towards getting additional compute from the cloud for bursting into cloud so that the project doesn't get delayed. But what happens to the data? The data also has to move along with the application. Otherwise, what are they going to work on? So those are the basic or important needs for customers today in business. So in this slide, this is where I was talking about the bottlenecks. So look at the compute. You run out of compute, add more number of compute. That's easy, right? But again, there is obviously a CapEx involved in it. You need to buy or purchase the servers before you can deploy them in production. But moving into cloud gives them the elasticity to grow and shrink the number of compute on demand, right? Scheduling. Now think about this. This is very important. In any EDA workloads, you will be having some kind of a scheduler. And one of the most popular ones is LSF, right? LSF is from IBM, and LSF is a scheduler. There's Slurm, there's PBS, there are a few others out there, but LSF is one of the most popular ones out there where most of the enterprises use. And I'll talk why I'm going to talk about LSF and scheduler. We do have an integration with that where customers are using their schedulers today on Pure Storage and the ability to control or manage the number of jobs. And why is it important, right? Yeah, scheduler is just going to schedule the number of slots for the jobs. The reason because the EDA license costs are tied directly in the number of slots you are using, the number of jobs that are submitted in the queue. So if your job is failing, or if your job is running for a very long time, it's a long running job, you're consuming a lot of EDA license costs. That's not a good way of optimizing EDA license cost. So we do have a better way of optimizing that cost from a scheduler perspective by making the scheduler smarter. That means it is checking the storage on demand using our REST APIs to figure out how much resources are available on the storage, what's the latency from the storage before submitting any new jobs. If it has already set a threshold and you're hitting the threshold value, then we do not submit any more jobs. That means the application is not going to submit any more jobs, and the queue is not going to be having any additional jobs for the storage for doing any I/O back to the backend endpoint, right? Networking I just talked about, and then obviously the storage, because storage has its limits, but Pure Storage with FlashBlade, we can scale out and scale up to a greater extent. We do also have our limits. Everything has its limits from a hardware perspective, but I think our limits are a lot more higher. Let's talk about the chip design workflow and tools for this for matter. Let me start giving you an idea today. EDA, as I said, it is a very diverse workload. It's got so many different tools. And if we just can take a look at this particular slide, we have different kind of workloads running on FlashBlade today in production. So we just cannot say that it is going to be just scratch or it is just one set of applications that is going to be running on FlashBlade. We have got build workloads. We have got software, design tools, software version control management like Perforce. They are running on Pure Storage. They've got flash arrays and FlashBlade. There's a dedicated validated architecture, and a lot of validation has gone behind that. As I said, if you have any direct questions for finding out on Perforce, please reach out to us directly. And then all about the performance, the different tools like Prime Time. And we also have got host-based tool like Rapid File Toolkit, where customers are using it today in production. So it's also in addition to various different parts of the workloads that can do various different functions from this toolkit. So overall, I think we have got a very comprehensive and very different kind of use cases today existing in production from various different EDA customers globally. Let's look into this workflow, the EDA workflow we've been talking about that so much right now. Let's say consolidating semiconductor workloads, right? What do you see in here on the left-hand side? There are various different parts of the workflow, right from software version control, that's where Perforce plays a role. You're doing build and RTL regressions. Build is something which you're doing during the verification phase, but we are doing regressions when you're doing tape outs. Then you have got simulations you're doing, then your synthesis and place and route, timing, power, noise, and then finally sign off and tape out. So this is the design part of it. Then again, from the foundries, that it starts from a sign on till all the way to the physical manufacturing of the chip. That is another phase that goes from the foundry part, right? But if you look at the compute layer, there is this particular job scheduler and all of these different kind of data that you see there, right from Verilog source code, the binary packages, to Scratch, to project data, EDA tools, libraries, and design data. All of them can reside on the FlashBlade over NFS. NFS is one of the most popular, version 3, I would say. NFS version 3 has been extremely popular choice of protocol right now from a file perspective. There are certain customers who use SMB, but the percentage of the footprint of SMB is very small, specifically in the design part. And there are some customers are also using NFS version 4.1 for security reasons, because there is a requirement for securing your entire data set, because NFS version 4.1 provides ACLs. ACL stands for Access Control List. ACLs provide you the capability of securing your access and authorization to files and directories. So that is also another way of using version 4.1. But if you look at the right-hand side, those orange boxes, right? If you look at this, those numbers and the qualifiers, those are the things which makes FlashBlade the best storage capable for handling EDA workloads, because it's got parallel access, it has high metadata. So as I said, the workloads in EDA are very diverse. There's some part of the workloads is going to be high on metadata, and some part of the workload is high on throughput. But we need to handle those kind of diverse workloads, and we can do that. Right from 30 million IOPS, again, these are all coded based on multi-chassis on our new platform, FlashBlade S, with a bandwidth up to 300 gigabyte per second read workload, which is, again, based on a block size of 512K. The fast delete is a huge attraction, because if you talk to any traditional storage vendor out there, if they ask them, hey, can I just go ahead and, what is your experience deleting millions of files? Because keep in mind, EDA is all about high file count. When you have a high volume of files, deleting them takes a very long time on any traditional storage. Whereas in FlashBlade, we do that completely in few seconds, and all of the files have been cleared by our back-end garbage collector, while the end user or the designer who is working on the particular workload or the project, they don't have to wait on the clients to respond back. They can get started at the front-end I/O, and the FlashBlade can still serve the data that is needed at the speed in which they would like for the project to run, whereas the back-end garbage collector is going to clean up. And that's a huge benefit for a lot of the customers, because then what is going to happen is they can run iterative processes or jobs or testing a lot more faster, and specifically when you're running regressions during tape outs. So when we're running into errors and you run to rerun it again, so you can clear up your entire environment and then start the test all over again. So that is where the fast delete works a great thing for them. High file count, because that's the important, because when you talk about high file count, it takes a lot of inodes. Now we have heard customers asking, specifically with the newer chip designs, which is generating millions and millions of files. They said, does your storage ever handle that high volume of inodes? Absolutely. We have got a tested limit, but I don't think we have any upper limit for the number of inodes we can handle. So the answer is we are capable of handling a lot of high inodes because of the high volume of files that has been generated in the newer platforms or newer chip design process and capacity. And believe me, the average data reduction for EDA workloads overall is 2:1. I have seen the lowest go all the way to like 1.2. But that is not something which you would see on average. I have also seen go all the way to like 5:1 or even 7:1. But those are rare scenarios. Those are like extreme ends of the spectrum. But I would say 2:1, I would be on an average, is a very comfortable data reduction that you normally see in an EDA workload. Now let's look into some of those performance numbers. Again, I do have the raw numbers. Those are not being published publicly. But if you do want to know more about the raw numbers, reach out to me directly. I can definitely share with them. And if you do want to share that with your customer, the customer has to be under NDA. Those numbers will be only shared under NDA. But I am trying to summarize what is the outcome of the various different tests we did on a 15-blade first generation flash blade, which is Norway, the 30-blade, which is a multi-chassis Norway, compared to a flash blade S that was launched last year with an S200 and an S500. So if you were to look into the graph on the right, you see those lines linearly, and there are 3 different EDA profiles that was tested, and those profiles are being generated using Spec Storage 2020, which is a benchmarking tool. And obviously these profiles are also very close to real EDA workload scenarios. We cannot be running on real data sets because we never find real data sets outside of the designer or the semiconductor or the foundries who use them because of the IP or intellectual property and security. So the only way we can do this is by simulating that workload. And Spec Storage 2020 is the closest benchmarking and load generator that is available today, which can run at scale. So we do have that, and Pure Storage, as a member of the spec committee, we constantly contribute to the profiles and update them, which is being up to date and endorsed by the spec committee. So if you look at those results, what you notice is from the various different storage endpoints that we tested, and the scalability for all the 3 profiles are clearly evident. Right from the left to the right, it is a scalable performance. Now, never I've been into the situations in customer conversations talking about scalable performance and linear growth. So the term linear may be misleading. When I say misleading, means customer may think, oh, it is going to be a slope of 45. No, that is not the case, because your growth or the slope could be a 30 or a 35. If you're lucky, you could be 45. But there is a linear growth, but the slope doesn't have to be 45. So keep in mind, whenever you're trying to show the particular linearity, and this particular in the graph that you see on the right-hand side, what you're seeing here is, in these profiles we were capturing during the verification phase, we were able to reduce the entire process time by 50%. That means the turnaround time, which was running at which was completing the jobs at 30 minutes on Norway, both on a single chassis and multi-chassis, dropped to 50% to 15 minutes on S200 and S500. So there is a 50% drop in the turnaround time, because I think that is a huge value to the end user. Because I can actually run as much amount of load to make the storage better, to show how much amount of IOP and throughput I can throw at the storage, or the storage can deliver. But what is important is the latency, and what is important is the turnaround time, how fast I'm completing the jobs at a very low latency. That's very important. And what we have found is that we were able to reduce that from 30 minutes to 15 minutes on the S platform. That's huge, right? And at the same time, what was also tracking was, whenever we were running this test on a Norway, single chassis or multi-chassis, we had a certain amount of cores. Like, for example, I'm just throwing out a number, but there is more information available in the white paper that has been published, but I'll just throw out a number. Like, for example, in a single Norway platform, we started off saturating at 350 cores. When we added another chassis, we went up to 550 cores, like another 200 cores, out of which after that, I'm still able to push more number of jobs and more number of I/O, but the latency is going up, right? And the turnaround time is also going up. So if I keep the turnaround time at 30 minutes, so I'm able to go from a 350 core on a single platform to 550 core on a multi-chassis Norway. Why am I telling this? Because this shows the amount of cores you can scale per platform. The limits are obviously higher, right? Now, when we went to S platform, S single chassis, S200, now I'm able to throw in about 600 in a single chassis, 600 plus cores on that one. And again, the details are there in the white paper. You can obviously look it up. And then when we went to an S500, we went close to 800 plus. So that is a huge difference from the number of cores that you can actually scale from a job, running the jobs a lot more faster. And when you're trying to throw in more number of cores, can the storage handle that? So it is not about the storage, it's all about the end user and the project and the life of the project, the active project that is going on. So that is very important, right? And the third important point is the data reduction. So what was earlier a 2:1 on a Norway platform, now the same data set was showing 2.6:1. So there is about a 30% improvement on the data reduction right there. All right, the other one was the regressions. It's about throughput, because you look into the throughput side again, we saw what we could do in IOPS, how the IOPS can scale. Now about throughput, because as I said, in an EDA workflow, if you remember from a previous slide, we had the verification phase, which is high on metadata. Then you have got your tape out phase, which is high on throughput because of large files. So when you're looking at the throughput, there's again a linearity in the various different profiles that we tested, right from a single chassis Norway all the way to the S500. So just to give you an indication, the tape out time also got reduced by 50%. So that is a huge way of showing that what the storage platform can directly influence or impact on the overall workflow. That's very important. Now, if I were to summarize on the IOPS to latency, if I were to take a look at the curve and I could do a comparison between the different platforms, either starting from a 15-blade first generation Norway to a 30-blade Norway, comparing that to an S200 and S500, if you notice, there is about a 4x improvement in IOPS from a single chassis Norway to an S500. Then there's a 2.2x between a multi-chassis Norway to an S500. And between S200 and S500, there's about a 75% I/O increment. And keep in mind, in every iteration of PureDFB that has been released, there has been optimization happening in the data path. There will be always some improvements happening from a performance perspective. So that is a good indicator, and it's a good progression that we'll be having moving forward as we start to release new versions of PureDFB on S500. And with multi-chassis, which is going to be happening fairly soon, the results will be having fairly soon, will determine how far we can actually scale when you go from a single chassis to a multi-chassis. I would say add another chassis and see that, and verify what the numbers look like. The second one is the bandwidth. This is again the one that we tested. So if you were to do a comparison between the bandwidth between Norway single chassis all the way to the S500, we saw about a 3x improvement in the bandwidth, the throughput, and then 75% improvement between the multi-chassis and S500, and about 40% improvement. Now, you must be wondering, these are all synthetic workloads. These have been done on the lab. But I'll tell you, ever since we have published these numbers, or at least sharing this information internally, I've been part of various different POCs going on at customers. And I am pleasantly surprised that the numbers that I have is very much aligned with what customers are getting. There's not a big difference. And that kind of gives me the confidence that the numbers and the test numbers we have got, the results based on the different EDA workload profiles we tested, is pretty much aligned with what the customer should be expecting. So if you were to share this information with the customer or in your customer engagements, I don't think you'll be completely misaligned with the performance numbers that we already have so far today on the new S platform. All right, now let's look about what happens after all this project, the workflow we talked about. Your project is ready, you're done with the blueprint, you're gone, send it back to your tape out, to your foundry, to the manufacturing part of it. What do you do with the project? Project is done. There's a lot of data that has been generated. Some of the scratch data may be deleted, they're all cleaned up, but there is a lot of data that is still there. You probably won't be needing all of them, but there are some data that can be repurposed, that can be reused for other projects, like IP, the intellectual property. But there are other parts of the data which doesn't have to be sitting on expensive S platforms, because there is a cost factor involved in it. As I said right in the beginning, it's all about cost optimization, performance, right? So how do I optimize the cost over here? And obviously when you're putting a lot of data sitting on an expensive platform, there's also consuming a lot of capacity and energy, right? And then obviously it impacts your overall ROI. So this is, again, another challenge we had for a very long time, but I think we have addressed that challenge now. Now with E, FlashBlade E, that is where E comes in, and if you look into this entire life cycle of data, right from active design projects to content repository where you move all your warm data, which is now going to be retired, not accessed that frequently. It'll be only accessed on demand on certain, there could be certain reasons for using it, otherwise most of the time it has not been touched, the data is sitting there. It's not entirely cold, well, your frozen cold data could be sitting in tape or maybe going into cloud, but I highly doubt most of the EDA or semiconductor design companies would actually get the data into cloud for long-term retention. So it always stays on premise. But what we were missing between the active hot data and the frozen data in tape was the intermediate layer or intermediate storage requirement to host or store the different the warm data, and that is what we are doing with E, FlashBlade E. Now let's look into a little bit of a data mobility part of a FlashBlade between S and E. We obviously know there is a bidirectional replication, so there is obviously you can move the entire file system from FlashBlade S to FlashBlade E. But a lot of the question comes is, okay, then what is my throughput? Is it impacting my front-end workload when I'm trying to move data between S and E? So those are the things we tested, and then we also looked into the customer says, well, I don't know what files to move. I can't move the entire file system. I would like to repurpose or reuse some part of the data. Is there a way I can pick and choose certain files to move over, and so that I can keep the remaining files in my active on this file systems on FlashBlade S? Yes, you can do that on our newly released Rapid File Toolkit, where you can actually do a pcopy or ptar, a bunch of files, and move it over from S to E. And those are also been tested. So if you really want to get some more insight on that, reach out to me and I can provide you all the information about Rapid File Toolkit and the new commands that we have introduced called ptar and pcopy. That is really very beneficial to customers who would like to be selective on the kind of files they would like to move from S to E. So just to summarize on the data lifecycle is the active project data that can move to archive after project is over. So it's basically you have got a hot tier and a warm tier, right? So new projects can start as old data can be moved from F to E, right? And then design data tools and libraries can be moved to F to E at an array at a host level after the project is completion. So that is a host level replication. We talked about Rapid File Toolkit. That gives you the ability to move files back and forth, and you all probably know that E has that ability to mount a file system directly over NFS or SMB. So that can be also done. And then chip design projects and data could be archived on all flash arrays for better cost efficiency. And that is the reason why we went with all flash. We don't deal with spinning media. And if you look into this entire, more and more conversations I'm having with customers, and if you look into the entire data lifecycle, it is making more sense because flash as it is getting cheaper day over day, day by day, so it is getting much more feasible to have data sitting there instead of spinning media. Why do you want to use spinning media when you can actually get cheaper and deeper flash storage? So that is where I think the data lifecycle makes a big full circle, and the way the data is been initiated or created during an active project, and all the way it ends up with E and then goes beyond E if that is needed. So this is another example of our efficiency or optimizing the EDA tool license. I was mentioning that earlier, but this is something which I would really like to talk about is the way you can use REST APIs to monitor or engage the particular FlashBlade resources. Like if you see here, it's a small Python script which has been included in an elim module. Now this is something to do with LSF. Elim is not something that you are going to be available every scheduler. Other schedulers may be having some other part, but I'm not aware of it. But I'm pretty sure that LSF, which is more popular, will be used also here in Korea, a lot of semiconductor companies. So you'd be using this particular module in the elim, which is called External Load Information Manager. These are using direct API calls to the FlashBlade to figure out what is the latency. Based on the latency information they gather from the FlashBlade, they would be determining to submit more jobs in the queue or not. That actually helps to optimize the way the scheduler functions and making it much more smarter and actually making the EDA tool license much more optimized because they don't have to submit jobs when the storage is completely bottlenecked and where it is going to either fail the job or slow down the job. And that is, in both the cases, not a good thing to do it. Now, just to wrap up, there's a lot of solutions around the EDA space, as I said, starting from Perforce, there is Synopsys workloads we have tested in cloud, in hybrid cloud, and obviously JFrog Artifactory is another binary tool manager, which a lot of EDA customers are using. I would say spend some time with your customers exploring or discovering the various different parts of the workloads. Just not focus on the storage alone. Storage is definitely what we are going to be selling into. But I would say understanding the workload and partnering with the customer on a journey that we can actually help them to optimize or use that particular infrastructure in a much better way. That should be the goal. And I think with all the different validations we have done, I think we can complete or touch upon the critical pieces right now. There will be a lot more we need to do, but I think we have got a lot of work on the performance and capacity at scale, the cloud, the hybrid cloud, data mobility. We have got good partnership with Comprise. So if you're dealing with anything like a hierarchical storage management, data tiering, reach out to us in corporate. We definitely can work with you to see how we can leverage the Comprise tool. We are partners with them. Right now, today, it is Meet in the channel. So if you want to get more information about it, reach out to us, to me or to Justin at corporate, and we can definitely help you with the process. Observability, that is another thing, because a lot of these EDA customers are now using standard tools where they would like to do monitoring and reporting. And Prometheus and Grafana has been a standard tool that they would be using, not rather than using storage proprietary tools, because every storage vendor has their own tools to do that. But they would like to have one standard pane of glass for managing all the endpoints. And they want us to provide APIs which can connect to the Prometheus and Grafana. We do have that available. There's a lot of documentation and best practices available to handle those kind of things, and you'll find it on the EDA webpage. And this is another layout for the entire hybrid cloud story. Again, there's a lot of details on hybrid cloud story. We can do this another session on this one altogether, but the idea is how when the EDA workloads start to burst into cloud for looking for more compute resources, how can we provide the storage SLA for the data that moves into cloud along with it, and the new data that has been generated during the part of the workload that has been running actively in the cloud. So those kind of things we have already done. Obviously, we have done this with Azure right now, and we can connect with AWS or other cloud providers too if that is a requirement. But I know in Korea, public cloud providers are not present. You are mostly using a Naver Cloud or a KT. But what the idea here is basically to show you that we can, if we do get an opportunity to have a FlashBlade in the data center to create a hybrid scenario, we can absolutely do that, because we have already validated that with a public cloud provider like Azure. We can possibly do the same thing with other local cloud providers here in Korea. All right, thank you very much for taking your time and listening to this entire EDA presentation. I would like to wrap this up with 2 or 3 data points. First of all, watch out for the EDA webpage. It is going to be updated pretty soon with a lot of good information, links to the white papers, demos. There's a lot of content coming out, and it is going to be the process throughout the year. But there is a lot of good marketing material happening, which gives you a top-down story, right from the workflow all the way to the storage. Number two, there will be a lot of events that we'll be participating, like the DAC that is coming up, Digital Automation Conference in San Francisco. There's supercomputing. Please invite your customers and ask them to visit the Pure Storage booth in those locations so that we can engage with them and in person, because I'll be probably there in both the locations. So we will be having a very healthy representation from the EDA community in the US from Pure Storage. So please let your customers know about these events that we are participating. And that's where I'd like to conclude this presentation. And if you have any questions, please reach out to me at bikash@purestorage.com. Thank you.